We'll have the tale of the two Thomases today. It's a tale concerning imaging, believe it or not, from ancient humans to the futuristic maybe stations and beyond the International Space Station. So our next presentation is by Dr. James Thomas, who is president-elect of the American Society of Echocardiography and staff cardiologist at the Cleveland Clinic, who will be presenting a study on modeling of the heart from echocardiography strain data collected on the International Space Station. Jim?
Okay, thanks very much, Bill. And I hope you didn't violate any HIPAA rules on revealing the princess's name there.
We do have permission from the Supreme Council of Antiquities for our IRB.
It's good enough for me.
There we go.
Well, moving from mummies to space, astronauts coming home from prolonged mission in space suffer a number of cardiovascular side effects, the most prominent of which is orthostatic hypotension. When they land on the ground, they very frequently cannot even stand up. They have severe fall in their blood pressure on standing, and that may take some days to reverse. And it sets up a scenario where, in the case of an emergency, astronauts simply could not be able to respond appropriately to that. So there's a lot of work to investigate why this orthostasis occurs. And there are several hypotheses. One is volume depletion, one is vasodilation, but a particularly interesting one is that the heart actually loses muscle mass in space. We know that the legs and the back lose muscle mass because they're not doing as much work, but also the heart doesn't do as much work in space. And so there is data from some earlier missions that there is a small but significant reduction in the mass of the heart and potentially in its pumping function. So in order to more fully investigate this problem, NASA has funded a large collaborative experiment called the Integrated Cardiovascular Study. It's funded by NASA, and my part of it is funded by the National Space Biomedical Research Institute. The overall study has as its PIs Ben Levine and Mike Bungo. And part of that study is to take astronauts who are currently going up to the space station, and we do comprehensive echo, stress echoes, tilt studies where we stand them up and see what happens to their blood pressure as well as their echoes, and do those all pre and post flight. Once they're in flight, though, we have an echo machine that was launched to the space station 10 years ago last month, and that's available for imaging the astronauts. We do this about once a month, and we have one exercise echo about halfway through the mission where they either do the bicycle exercise or rowing or something like that, and then very quickly get imaged. And through the NASA Science Network, I can log on and actually see these images being obtained, and through the capsule communicator get some guidance as to how to change the image and stuff to optimize the imaging there. Those data then come down to the ground for analysis to see what really is happening to the heart in space there. The critical thing that we're looking at, there are a number of parameters, but one of the most interesting ones and one of the most sensitive for early dysfunction of the heart is something called strain. And strain, in its simplest notion, is just the percentage change of a length of tissue. So if you had a rubber band that was 10 centimeters long, you stretched it to 11, that would be a 10% strain there. And it turns out that in a variety of conditions like cancer chemotherapy, early heart failure, early coronary disease, diabetes, there's a reduction in this strain parameter. So it's one we think could be very helpful for looking at the astronauts. And we're looking at that pre and post flight in those echoes. The problem is the echo machine that's on the space station is sort of the state of the art circa 1997. And back then they had never heard of strain by echocardiography. So the real purpose of this study was to see whether we can extract strain measurements out of those old echo images for comparison with the pre and post flight experiments. Now, this sounds like an incredibly small problem because, you know, how many astronauts really are there? But it actually has a very broad utility in echocardiography today because there is evidence that strain obtained by a number of the different vendors actually do not agree well with each other. So you can't take a patient studied on one machine, bring them back a year later, have them studied on another machine, and know whether those numbers really line up together. And so this is actually a much broader issue within echocardiography. So to address both the NASA issue and the general imaging issue, we've designed a study where we're taking a number of patients, imaging them on contemporary echo machines, imaging them on the old HDI 5000, which we have still in our laboratory from our early NASA work, and then analyzing them with a variety of software tools. There are tools that are specific to each vendor, and then there's sort of vendor-neutral tools that are able to extract the data from a more generically stored image. And what we have found, and this has required some iterations with the software development to make sure we can really track the images appropriately, but it does appear that there is good correlation between the two strain measurements. The work is ongoing, but at least between two of our vendors there, we had a correlation of 0.91, which is really quite good for this type of an examination there. And so the data, once they are extracted into strain, and then the structural data is also there, we are feeding this into a modeling exercise. We have a group of scientists both at the NASA facility in Cleveland and also at the University of Auckland in New Zealand. And the folks in Auckland have a premier modeling group down there, and they have done some very comprehensive modeling of the heart. And so by taking the strain and structural data from that and feeding it into their existing model and then modifying it on the basis of these new data, they should be able to come up with sort of an archetypal astronaut's heart and simulate what happens over 3 months, 6 months, 12 months in space as we go out into longer and longer missions, including Mars and beyond. This also will have great utility in general cardiology, though, because we're also modeling congestive heart failure and regional coronary disease and all manner of diseases like that. And so I think that this is a small piece of that puzzle. We have probably another 2 or 3 years to go on the integrated cardiovascular study before we'll have the definitive word on the impact of long-term spaceflight on the heart. But I think this piece has given us good encouragement that we'll be able to extract the most information we can from these existing echocardiograms, as well as move strain imaging more into the mainstream of clinical cardiology.
Thank you, Jim.